Greetings from Team ARES Robotics. We are a group of 25 undergraduate students from Netaji Subhas University of Technology, and we are proud to present our rover, Chandrashekhar.
The mechanical team is responsible for designing, fabricating, and assembling various components of the rover. To ensure a lightweight yet durable structure, we use aluminium 6063 T6 for every structural component. We have installed a customized double rocker suspension system with 4 wheels that provides optimal stability and extreme traversal capabilities, ensuring maximum contact. The rover's chassis features an ultimate stability provider differential bar that offers high ground clearance and minimizes the risk of toppling. Additionally, we use polyurethane balloon tires. These tires have a cushioning effect and a skid steering design that provides superior movability on rough terrain. The 5 degrees of freedom articulated manipulator is fabricated using laser-cut aluminum linkages. It features 2 actuators and DC motors with encoders implemented with inverse kinematics. It thus provides higher dexterity and can lift a payload up to 5 kgs. The end effector comprises a lead screw-based gripper for pitch roll and gripping action that provides precision and versatility. A NEMA 23-stepper motor is used for base rotation that provides 360-degree rotation to the robotic arm. For the extreme retrieval and delivery task, GNSS coordinates will be entered into the GUI, followed by the ROS2 system charting a course using a global planner to the location. The local planner will make smaller trajectory adjustments for object avoidance. Thereafter, with the help of our arms gripper, we can connect and deliver the object to the specified location.
Here we present to you our electronic system which has been designed with a modular approach. Our system has been divided into 6 subsystems, namely propulsion, arm control, science control, main processing unit, EPS and communication. By dividing the system into these separate subsystems and placing them into individual boxes, we have made debugging and connections easier and faster assembly possible. To drive all of our subsystems, we have opted for a high-performance CPU, Jetson Xavier, which allows us to integrate all the subsystems effectively and ensures optimal performance. The 26-volt lithium-ion battery is the power source that drives heavy loads, whereas the secondary battery is used in the electronic system. To ensure that the power supply is reliable and consistent, 11 AWG wires has been used to carry high current operations. This helps us prevent any chances of heating and damage to the system. To ensure smooth and reliable transmission between the rover and the control station, we have equipped it with both the 5.8 GHz TP-Link CPE and the 2.4 GHz binatone CPE. The binatone CPE with its 12 dBi omnidirectional antenna is the perfect choice for transmitting command signals with remarkable accuracy and speed. With a range that extends up to 2.4 km, we can remotely control the rover with ease even in the most challenging terrains. To receive real-time video data from the rover, we are utilizing the 5.8 GHz TP-Link CPE. This system boasts a large bandwidth, allowing for seamless and faster communication and streaming. The rover is also equipped with a kill switch, which when triggered will turn off the propulsion system. However, the communication system will remain operational.
The objective of the science and research team is to focus on the detection of extinct, extant and no life and to drive advances in the field of human space exploration. To detect the presence of life on Mars, we have employed 4 different biochemical tests on our onboard life detection system, which are Schiff's test, Sudan 4 test, Mollis test, and Bradford test. These tests gives us information about the presence of proteins, lipids, carbohydrates, which are essential biomarkers of extraterrestrial life. To collect and transport the soil samples, we take the help of a science sampling system, which comprises of an auger-based drill for loosening the soil, which is then transferred to the blender with the help of a blower and a vacuum system. Thereafter, a slurry solution is created in the blender, which is then transferred to the test tubes and cuvettes for chemical testing. For a more detailed analysis of the samples, the science team is working to create a custom UV visible spectrophotometer and have created a custom visible spectrophotometer, which is powered by a high voltage supply, and we have tested the spectrum of a warm white LED with the help of it. Along with this, a rock sample is collected and transferred to a container attached on a chassis so that it can be brought back to the base station for further testing. To study the various parameters of planetary habitability, we have integrated our rover with several soil and gas sensors to study the subsurface and atmospheric properties. For this, we have incorporated our rover with pH, methane, ammonia, moisture, temperature, and atmospheric pressure sensors. To study the distribution of rocks and minerals on Mars, we have trained datasets of different rock samples to predict the properties of an unknown sample and to study the pattern of biosignatures with the help of a CNN model. For this, we have integrated our rover with a microscope which provides us with the images of the rock samples.
The GUI shows sensor and video data and allows teleoperation and autonomous mode toggling. ARES provides more detail on cost maps and trajectories. The rover uses a ROS2 localization pipeline that estimates its position and orientation using sensor data from an Intel RealSense camera for RGBD data and an IMU for orientation data. The pipeline generates hypotheses for the rover's position and orientation using a particle filter algorithm, which are updated using sensor data. The navigation stack then uses the estimated position and orientation information to plan paths and avoid obstacles. The global planner generates a path that avoids obstacles by taking into account the rover's constraints and environment's characteristics, while the local planner executes the plan in real time, using the rover's sensors to track its position and adjust the trajectory if necessary. We have used the augmented reality library, Aruko, for pose and gate detection, which enables us to locate and identify markers in the global route so that the path planning algorithm can output commands accordingly.